Hi everyone, I am Whit Roy. Today I will review Apprentice Mirrors Electronics test paper. First I will show all the test questions on the screen. You can have a try yourself. Then I will go through Mirrors paper. For each question I will explain why the correct answer is right and why the other options are wrong. I hope you enjoy this style of learning. First, let's start this electronics topics test. 3, 2, 1, go. Okay, Mira, thanks for sitting down with me. You've just finished the basic electronics and semiconductor devices quiz. There were 51 questions.
Yeah, I knew some of them, but I got pretty lost once the rectifiers and diode ratings started mixing together.
Your result was 26 correct and 25 wrong, so the quiz is recorded as a fail. That's disappointing, but it gives us a very clear revision plan.
Nearly half wrong, that's worse than I expected.
Don't focus only on the number. We'll put your paper on screen and go through every question. Where you were right, I'll confirm the key reason. Where you were wrong, we'll slow down and rebuild the idea step by step.
Okay, I'd like to know why the other choices are wrong as well.
Good, that is how you stop guessing in the real exam. Let's begin. Question 1. What is the purpose of a reverse bias Zener diode connected across a DC load?
I picked to interrupt normal current as a fuse. I think I saw the word protection and treated the Zener like an overcurrent device.
I can see why you picked that, but it is not the right one. Let's work through it. A Zener used across a DC load is not a fuse.
So it does not open the circuit when the voltage rises?
No, it begins to conduct in a controlled way. Now, step 1, it is reverse biased. Step 2, below its Zener voltage, it carries very little current. Step 3, near its rated breakdown voltage, it conducts and holds the load voltage close to that value. A series resistor or other current limiting arrangement is still required.
So I should choose to regulate or limit the voltage across the load.
Yes, that's it. In its breakdown region, a Zener diode holds the load voltage close to its rated Zener voltage.
Right, I had put it in the fuse category. The voltage regulating part is what I missed.
Question 2. What do the initials BJT mean in semiconductor electronics?
I selected bipolar junction transistor.
Yes, you got that one. BJT means bipolar junction transistor, a 3-terminal semiconductor device commonly used for amplification or switching.
Yes, that abbreviation came back straight away.
Question 3. Where is a VDR normally connected to protect equipment from a voltage surge?
I put it in series with the load. I was thinking the surge had to pass through the VDR before it could reach the equipment.
Okay, this is one of the questions where the wording can pull you the wrong way. Start with the basic operation. A VDR is normally placed in parallel. At normal voltage, its resistance is high, so it draws very little current. During a surge, its resistance falls sharply, and it diverts surge current away from the protected equipment. In series, it would carry normal load current, and would not clamp the voltage in the intended way.
Okay, I think I've got it. The answer is in parallel with the circuit or component being protected.
Good, you've got the important point now. A VDR is connected across the supply or protected component so that it can clamp an excessive voltage.
Starting with the normal voltage condition makes the parallel connection easier to remember.
Question 4. If sensitive electronic equipment cannot be disconnected before an installation insulation resistance test, what is the most appropriate action?
I chose increase the insulation test voltage until the equipment operates. Saying it aloud now, that sounds unsafe. I think I misunderstood what the test was trying to prove.
Not quite. Let's pause there and picture what the component is doing. That would increase the chance of damage. First, disconnect or isolate sensitive electronics where practicable. If disconnection is impracticable, follow the manufacturer's instructions and use an approved alternative or reduced voltage test arrangement. The purpose is still to assess insulation without applying a destructive test voltage to semiconductor inputs.
So, putting those steps together, it should be use an approved alternative test method that will not damage the equipment.
That's right. An approved alternative method or suitable reduced test arrangement should be used when disconnection is impracticable.
Right. The safe test method matters more than simply remembering the tester's name.
Question 5. What is the purpose of thermal compound applied between a semiconductor and its heatsink?
I selected to fill microscopic air gaps and improve heat transfer.
That answer is right. Thermal compound fills small surface gaps, reducing thermal resistance between the device and heatsink.
I'll remember the tiny air gaps. That makes the purpose of the compound quite practical.
Question 6. Which events can produce transient overvoltages on a power supply circuit?
I selected the steady resistive load. I wasn't clear about what the word transient meant, so I went for the only load condition I recognized.
I understand your thinking, but that answer reverses the actual operation. We'll build it up one step at a time. A steady resistive load is not normally a transient source. Lightning can inject a sharp surge. Opening an inductive circuit can produce a voltage spike as its magnetic field collapses. Supply network switching can also cause short duration overvoltage. The key word is transient, a brief, rapid change.
Right. Then the correct choice is lightning activity, switching an inductive load, and operation of switching devices on the supply network.
Yes, keep that reasoning with the answer. Lightning and switching operations can cause short-duration voltage spikes. A steady resistive load normally does not.
I see it now. A transient is the brief change, not the normal steady condition.
Question 7. How many diodes are normally used in a three-phase full-wave bridge rectifier?
I selected 6.
Good, no problem with that one. A three-phase full-wave bridge has an upper and lower diode for each of the three phases, giving 6 diodes.
Yes, 3 phases with an upper and lower diode for each phase gives 6.
Question 8. Which devices can protect semiconductor components against transient overvoltages?
I went with a thermal overload relay. My thinking was that it protects equipment, but I didn't separate overheating protection from surge protection.
Well, that choice sounds possible at first, but it does not fit the circuit. Let's check the key facts. A thermal overload relay responds mainly to sustained overcurrent and heating. It is not a voltage clamping device. A VDR, or a suitable Zener or transient suppression diode, conducts when voltage rises beyond its designed level. That limits the voltage seen by the semiconductor.
Let me say it back. The answer is a voltage-dependent resistor and a Zener or transient suppression diode.
Yes, your choice is correct. That is the distinction the question is testing. VDRs and suitable Zener or transient suppression diodes limit voltage spikes by conducting when the voltage reaches a specified level.
Next time I'll ask whether the device is meant to clamp voltage or respond to heating.
Question 9. In a half-controlled full-wave bridge rectifier, how is the average load voltage controlled?
I answered by changing the polarity of the diodes. I knew something in the bridge had to be controlled, but I chose the wrong devices.
That one needs another look. Don't try to memorize the sentence yet. Follow the current or voltage first. The ordinary diodes are uncontrolled. Their polarity is fixed.
Then the part I can adjust must be the SCRs?
Yes, the SCRs are the controllable devices. A gate pulse is delayed by a chosen firing angle in each half cycle. Earlier firing gives a longer conduction period and a higher average load voltage. Later firing gives a shorter period and a lower average voltage.
I see, so I need by changing the firing angle of the SCRs.
Good. Now the answer follows from the operation rather than from guessing. Delaying or advancing the SCR gate pulses changes the portion of each half cycle applied to the load and therefore changes the average output voltage.
Following the firing angle through one half cycle makes it much less abstract.
Question 10. What is the function of a transducer?
I selected to convert energy or a physical quantity from one form into another.
That one is correct. A transducer converts one form of energy or physical quantity into another, commonly converting a measured condition into an electrical signal.
Converting one physical quantity into another was the clue for me.
Question 11. Which statements correctly describe thermistors?
I chose their resistance is unaffected by temperature. I mixed thermistors up with ordinary fixed resistors.
You have mixed up two different functions there. That's all right, let's separate them. Temperature dependence is the whole purpose of a thermistor. For an NTC device, temperature up means resistance down. For a PTC device, temperature up means resistance up. Remember, the first letter describes the sign of the temperature coefficient, not the physical size of the device.
Okay, not the option I chose. It should be, their resistance changes with temperature. An NTC thermistor's resistance decreases as temperature rises, and a PTC thermistor's resistance increases as temperature rises.
Yes, exactly. A thermistor is temperature sensitive. NTC and PTC types have negative and positive temperature coefficients respectively.
Right, I forgot that changing resistance with temperature is the main feature of a thermistor.
Question 12. Which methods help transfer heat away from a power semiconductor?
I selected using a correctly sized heatsink.
You read that question properly. A heatsink, good thermal contact, and adequate airflow reduce the semiconductor junction temperature. This was a multiple answer item. You correctly identified all of these. Using a correctly sized heatsink, applying thermal compound between the device and heatsink, and providing suitable ventilation or forced air cooling.
Right, a heatsink, thermal compound, and good airflow all help remove heat from the semiconductor.
Question 13. Why is rectified three-phase AC generally easier to smooth than rectified single-phase AC?
I put one output pulse per cycle. I was still picturing a single-phase half-wave circuit instead of 3 separate phases.
Close in wording, but not in operation. Okay, let's slow the idea down. A three-phase full-wave bridge is a 6-pulse rectifier.
6 pulses in every supply cycle?
That's right. Its pulses are closer together than those of a single-phase rectifier, so the output has less time to fall between peaks. At 50 Hz, the ripple is 300 Hz. Higher ripple frequency and smaller gaps make filtering easier.
That means the correct answer is, its ripple frequency is higher, and its output falls by a smaller amount between successive pulses.
That's the one. The more frequent overlapping three-phase pulses give less variation in output voltage, allowing filters to smooth the output more effectively.
All right, I could now explain why the selected option is right, not only recognize it.
Question 14. Which statements correctly describe a single-phase full-wave bridge rectifier?
I selected it uses both half cycles of the AC input.
Right answer. A bridge rectifier reverses the connection of each input half cycle so that load current keeps the same direction. A center tap is not required. This was a multiple answer item. You correctly identified all of these. It uses both half cycles of the AC input, and load current flows in the same direction during both half cycles.
Good. I can now picture different diode pairs keeping the load current in the same direction.
Question 15. Which statements correctly describe filtering at a rectifier output?
I said filtering increases the ripple. I think I confused filtering with adding more pulses to the waveform.
I can see why you picked that, but it is not the right one. Let's work through it. Filtering is intended to reduce ripple. A capacitor charges near the voltage peaks, then supplies the load while the rectified voltage falls. A resistor can be combined with the capacitor as an RC filter, and an inductor may also be used. Stored energy fills the gaps between rectifier pulses.
Ah, so I should choose. A capacitor can store energy when the output voltage rises. A capacitor can supply load current as the rectified voltage falls. And a resistor may be combined with a capacitor to form an RC filter.
Yes, that's it. Capacitors charge and discharge to reduce voltage variation, and resistors or chokes may be combined with them for additional filtering.
I see. Filtering stores energy and fills the gaps between pulses, so it reduces ripple.
Question 16. Which diode arrangement provides single-phase full-wave rectification without requiring a center-tap transformer secondary?
I selected a 4-diode bridge rectifier.
Good, you recognize the key idea. A 4-diode bridge uses the complete transformer secondary on both half cycles without a center tap.
I remembered that relationship from the earlier rectifier work.
Question 17. What is the main advantage of a Zener diode compared with an ordinary rectifier diode?
I selected it is designed to operate safely at a specified reverse breakdown voltage.
Yes, you got that one. A Zener diode is designed for controlled reverse breakdown operation, allowing it to provide voltage regulation or overvoltage limiting.
Yes, I could explain that without relying on the wording of the options.
Question 18. During which condition is the peak inverse voltage applied to a diode in a rectifier?
I picked the forward biased condition because that sounded like the greatest electrical stress. I didn't stop to separate current stress from reverse voltage stress.
Okay, this is one of the questions where the wording can pull you the wrong way. Start with the basic operation. PIV concerns reverse voltage, not forward current. When another diode or diode pair conducts, the non-conducting diode can be reverse biased. The largest reverse voltage appearing then is the peak inverse voltage that the diode must withstand without breakdown.
Okay, I think I've got it. The answer is when the diode is reverse biased and blocking current.
Good, you've got the important point now. A non-conducting rectifier diode is reverse biased and must withstand the peak reverse circuit voltage.
Right, PIV occurs while the diode is reverse biased and blocking current.
Question 19. Why can opening the circuit to a relay coil or contactor coil produce a high transient voltage?
I answered that the coil becomes a permanent short circuit. I knew the collapsing field causes a problem, but I guessed the result rather than following the voltage.
Not quite. Let's pause there and picture what the component is doing. A coil stores energy in its magnetic field. When current is interrupted, the field collapses. By Lenz's law, the induced voltage opposes the rapid fall of current, so the voltage can become very high. A flywheel diode RC snubber, or VDR, can provide a safer path for that energy.
So putting those steps together, it should be, the collapsing magnetic field induces a voltage that opposes the current change.
That's right. An inductive coil resists a rapid current change, so its collapsing magnetic field can generate a high voltage.
I understand. The collapsing magnetic field produces the high voltage across the coil.
Question 20. What is likely to happen if the reverse voltage across a diode exceeds its PIV rating?
I selected the diode may enter reverse breakdown and be damaged.
That answer is right. Exceeding the PIV rating can cause reverse breakdown, excessive current, and permanent diode failure.
All right, I don't need to spend much revision time on that one.
Question 21. A three-phase full-wave bridge rectifier is supplied at 50 Hz. What is its output ripple frequency?
I chose 150 Hz. I multiplied the supply frequency by 3 phases, but I'm not sure whether I also needed to account for full wave operation.
I understand your thinking, but that answer reverses the actual operation. We'll build it up one step at a time, count pulses, then multiply. A three-phase full-wave bridge gives 6 output pulses in each supply cycle. 6 times 50 Hz equals 300 Hz. The 150 Hz answer would correspond to only 3 pulses, which is a three-phase half-wave pattern.
Right, then the correct choice is 300 Hz.
Yes, keep that reasoning with the answer. A three-phase full-wave bridge is a 6-pulse rectifier, so the ripple frequency is 6 times 50 Hz equals 300 Hz.
6 pulses per cycle at 50 Hz gives a ripple frequency of 300 Hz.
Question 22. What does peak inverse voltage mean for a rectifier diode?
I selected the maximum reverse voltage the diode can withstand without breakdown.
Good, no problem with that one. PIV is the highest reverse voltage that may be applied without causing reverse breakdown.
That one felt familiar, so I didn't need to guess.
Question 23. A single-phase full-wave rectifier is supplied at 50 Hz. What is its output ripple frequency?
I selected 100 Hz.
Yes, your choice is correct. Full-wave rectification produces 2 output pulses per supply cycle, giving 2 times 50 Hz equals 100 Hz.
Right. Full wave rectification gives 2 output pulses per cycle, so 50 Hz becomes 100 Hz.
Question 24. Why must the junction temperature of a power semiconductor be kept below its maximum rating?
I selected excessive junction temperature can permanently damage the device.
That one is correct. Excessive junction temperature can alter semiconductor characteristics and cause rapid or permanent failure.
I see. Excessive junction temperature can permanently damage the semiconductor.
Question 25. What are the purposes of the series resistor in a simple Zener diode voltage regulator?
I selected to increase the supply ripple frequency. I remembered that the circuit changes the output waveform, but I attached that idea to the wrong purpose.
Well, that choice sounds possible at first, but it does not fit the circuit. Let's check the key facts. The resistor does not change supply frequency. It drops the voltage difference between the supply and the Zener regulated output, and it limits current. Using Ohm's law, its current is approximately supply voltage minus Zener voltage divided by resistance. Without it, excessive Zener current could destroy the diode.
Let me say it back. The answer is to limit the current through the Zener diode and to drop the excess supply voltage.
You read that question properly. That is the distinction the question is testing. The resistor drops the difference between supply and regulated voltage and limits current to a safe value for the Zener diode and load.
Right, the resistor limits Zener current and drops the excess supply voltage.
Question 26. What happens during the opposite half cycle in a single diode half-wave rectifier?
I selected the diode is reverse biased and blocks load current.
Right answer. During the unwanted half cycle, the diode is reverse biased, so ideally no load current flows.
During the opposite half cycle, the diode blocks, so there is almost no load current.
Question 27. What transformer secondary arrangement is suitable for a basic 3-phase half-wave diode rectifier requiring a neutral return?
I chose the delta secondary with no neutral. I noticed it was a 3-phase question, but I didn't think about where the return path would be.
That one needs another look. Don't try to memorize the sentence yet. Follow the current or voltage first. A basic 3-phase half-wave rectifier needs a return path from the load to the source star point. Therefore, the secondary must be star connected with an accessible neutral. A delta winding has no neutral point, so that simple 3-diode half-wave arrangement cannot obtain its required neutral return.
I see, so I need a star-connected secondary with an accessible neutral.
Good, now the answer follows from the operation, rather than from guessing. A 3-phase half-wave rectifier normally uses 1 diode per phase and requires a neutral return from a star point.
Right, the 3-phase half-wave circuit needs a star-connected secondary with an accessible neutral.
Question 28. What is the main function of a capacitor connected across a rectifier output?
I selected to charge near voltage peaks and supply the load between peaks.
Good, you recognize the key idea. The capacitor stores energy at the rectified voltage peaks and releases it between peaks, reducing output ripple.
No problem with that one. The waveform made the answer fairly direct.
Question 29. Why can an insulation resistance test damage semiconductor equipment connected to an installation?
I chose the answer about excessive load current. I was thinking of the tester forcing a large current through the equipment, which I now suspect is not how an insulation tester works.
You have mixed up two different functions there. That's all right, let's separate them. An insulation tester is designed to apply a relatively high DC test voltage while limiting current. The main risk is voltage stress, not ordinary load current. The test voltage may exceed the rating of semiconductor junctions, suppression components, or control inputs, so sensitive equipment must be isolated or tested by an approved alternative method.
Okay, not the option I chose. It should be, the test voltage may exceed the voltage rating of semiconductor components.
Yes, exactly. An insulation resistance tester can apply a high DC voltage that exceeds a semiconductor device's rating.
I understand. The insulation tester may apply a voltage high enough to damage the semiconductor components.
Question 30. What is the main filtering action of a choke connected in series with a rectifier load?
I confused the choke with a smoothing capacitor. I thought the component would bypass the AC ripple and leave the DC at the load.
Okay, that describes the action of a capacitor connected across the load, but this question asks about a choke connected in series. A choke is an inductor. It allows the steady DC load current to pass, but its inductive reactance opposes the changing AC ripple current. This reduces the ripple and makes the load current smoother.
So the correct answer is that the choke opposes changes in load current and reduces the ripple current.
Correct. Remember, a capacitor is connected across the load to bypass ripple, while a choke is connected in series to oppose ripple current.
Right, the choke opposes changes in current and therefore helps smooth the load current.
Question 31. Which statements describe the output of an unfiltered single diode half-wave rectifier?
I selected it is a pulsating DC waveform.
Yes, you got that one. Half-wave rectification uses one input half cycle, giving pulsating DC at the supply frequency. This was a multiple answer item. You correctly identified all of these. It is a pulsating DC waveform and only one half of each input cycle is used.
That matches the waveform I had in mind.
Question 32. How should a diode's reverse voltage rating compare with the maximum PIV imposed by its circuit?
I selected half the circuit PIV. I treated the rating like a shared value between two diodes instead of a limit that each diode must withstand.
I can see why you picked that, but it is not the right one. Let's work through it. The diode must survive the maximum reverse voltage imposed by the circuit. Its rated reverse voltage, therefore, has to be greater than the calculated PIV, with a suitable margin for supply variation and transients. A rating below PIV risks reverse breakdown.
So I should choose. The diode rating must be higher than the circuit PIV with a suitable margin.
Yes, that's it. The selected diode must safely withstand the maximum circuit PIV, including an appropriate design margin.
The diode rating must be higher than the maximum reverse voltage it will experience.
Question 33. Which components are commonly used in a rectifier, smoothing, or filter circuit?
I selected capacitors.
That answer is right. Capacitors, inductors, and resistors may be arranged as filter networks to reduce the AC ripple in a rectified DC output. This was a multiple answer item. You correctly identified all of these: capacitors, inductors, and resistors.
Right, capacitors, inductors, and resistors can be combined to reduce ripple.
Question 34. Where is a smoothing capacitor normally connected in relation to the load of a rectifier?
I selected in parallel with the rectifier load.
Good, no problem with that one. A smoothing capacitor is normally connected across the DC output load so it can store and release charge.
I'm confident with that one because I know what happens on each half cycle.
Question 35. A single-phase half-wave rectifier is supplied at 50 Hz. What is its output ripple frequency?
I selected 50 Hz.
Yes, your choice is correct. A half-wave rectifier produces one output pulse per supply cycle, so its ripple frequency equals the 50 Hz supply frequency.
I'll keep that in the strong column and focus on the rectifier calculations.
Question 36. Which statements describe three-phase diode rectification?
I put all 6 diodes conducting together. I saw 6 diodes in the bridge and assumed the whole bridge operated at once.
Okay, this is one of the questions where the wording can pull you the wrong way. Start with the basic operation. A three-phase half-wave rectifier normally has 3 diodes. A full-wave bridge has 6 diodes and produces 6 pulses per cycle, but only 2 normally conduct at one instant, one from the most positive phase to the load and one from the load to the most negative phase.
Okay, I think I've got it. The answer is a 3-phase half-wave rectifier normally uses 3 diodes. A 3-phase full-wave bridge normally uses 6 diodes, and a 3-phase full-wave bridge produces 6 output pulses per supply cycle.
Good, you've got the important point now. Half-wave uses 3 diodes, while a 6-diode bridge gives 6-pulse full-wave rectification with 2 diodes conducting at a time.
I think I could talk someone through that current path now.
Question 37. Which statements correctly compare a center-tapped full-wave rectifier with a bridge rectifier?
I selected the center tap circuit normally uses 2 rectifier diodes.
That one is correct. Both circuits provide full-wave output, but the center-tapped arrangement uses 2 diodes and a center-tapped secondary, while a bridge uses 4 diodes. This was a multiple answer item. You correctly identified all of these. The center-tapped circuit normally uses 2 rectifier diodes, and the bridge circuit normally uses 4 rectifier diodes.
Good, I could picture the component while I answered.
Question 38. Which conditions can turn off an SCR after it has been triggered?
I chose a larger positive gate current. I remembered that the gate turns an SCR on, so I assumed more gate current would also turn it off.
Not quite. Let's pause there and picture what the component is doing. A conventional SCR gate can turn the device on, but it cannot normally turn it off. After latching, the anode current must fall below the holding current, or the SCR must be reverse biased by commutation. More positive gate current will not interrupt the anode current.
So, putting those steps together, it should be its anode current falls below the holding current and the SCR becomes reverse biased.
That's right. An SCR turns off when current falls below its holding value or when commutation reverse biases it. The gate does not normally turn off a conventional SCR.
I see. An SCR turns off when its anode current falls below the holding current or is forced to 0.
Question 39. Which statements apply to a center-tap single-phase full-wave rectifier?
I selected both half cycles contribute to the output.
You read that question properly. A center-tapped full-wave rectifier uses both input half cycles and produces 2 output pulses per supply cycle. This was a multiple answer item. You correctly identified all of these. Both half cycles contribute to the output, and its ripple frequency is twice the supply frequency.
Okay, I can use that reasoning if the wording changes in another question.
Question 40. Which circuit conditions should be considered when selecting the required reverse voltage rating of a rectifier diode?
I picked the enclosure color. Honestly, that was a guess. I had forgotten which practical conditions actually affect semiconductor temperature.
I understand your thinking, but that answer reverses the actual operation. We'll build it up one step at a time. Reverse voltage selection is electrical. Start with the transformer secondary peak voltage, then account for the rectifier arrangement because different circuits impose different PIV. Finally, allow for supply tolerance and transient overvoltage. Enclosure color has no bearing on diode voltage stress.
Right, then the correct choice is the transformer secondary peak voltage, the rectifier configuration, and possible supply variation and transient overvoltage.
Yes, keep that reasoning with the answer. Circuit peak voltage, rectifier arrangement, supply tolerance, and transients all affect the required reverse voltage rating.
Right, I must consider both the normal supply voltage and any transient or switching voltages.
Question 41. What is the main function of a voltage-dependent resistor, VDR?
I selected to limit transient overvoltages.
Right answer. A VDR is used as a surge suppressor. It limits short-duration voltage spikes that could damage insulation or electronic components.
Yes, I knew that definition and could rule out the other choices.
Question 42. What precautions should be taken before insulation resistance testing a circuit containing sensitive electronic equipment?
I selected disconnect or isolate the sensitive electronic equipment.
Good. You recognize the key idea. Sensitive equipment should be isolated where necessary, and the manufacturer's instructions must be followed. This was a multiple answer item. You correctly identified all of these. Disconnect or isolate the sensitive electronic equipment and follow the equipment manufacturer's testing instructions.
I understand. Sensitive equipment should be disconnected, isolated, or tested using an approved safe method.
Question 43. Which measures can minimize semiconductor damage caused by transient voltages?
I answered that the overcurrent protection should be removed. I thought that might stop nuisance operation during the test, but it doesn't sound like a safe precaution.
Well, that choice sounds possible at first, but it does not fit the circuit. Let's check the key facts. Removing overcurrent protection creates another hazard and does not control voltage spikes. Suitable measures include a surge protection device, a suppression diode across a DC coil, or a correctly rated RC snubber or VDR. Each provides a controlled route for transient energy or clamps the voltage.
Let me say it back. The answer is fit a suitable surge protection device, connect a suppression diode across a DC inductive coil, and use a correctly rated RC snubber or VDR where appropriate.
Yes, you got that one. That is the distinction the question is testing. Surge protective devices, suppression diodes, snubbers, and VDRs limit or absorb damaging transient energy.
That clears up the mix-up. I had the correct family of protection in mind, but the wrong operation.
Question 44. A rectifier circuit can impose a maximum reverse voltage of 340 V on each diode. Which diode is the most suitable based only on reverse voltage rating?
I chose the 300-volt diode because it matched the stated voltage exactly. I didn't allow any margin above the required PIV.
That one needs another look. Don't try to memorize the sentence yet. Follow the current or voltage first. The circuit can impose 340 volts, so a 300-volt diode is already below the required withstand value. The 600-volt diode exceeds 340 volts and gives a useful margin. Selection must also consider current and other ratings, but based only on reverse voltage, 600 volts is the suitable choice.
I see. So I need a diode rated at 600 V reverse voltage.
Good. Now the answer follows from the operation rather than from guessing. A 600V diode exceeds the 340V circuit requirement and provides a reasonable voltage margin.
Right, the diode must be rated above 340 volts, so 400 volts is the suitable choice.
Question 45. What will turn off a conducting SCR in a DC power circuit?
I selected another positive gate pulse. I was treating the gate as an on and off control, like a transistor input.
You have mixed up two different functions there. That's all right. Let's separate them. Once an SCR has latched, removing or repeating the gate signal does not stop it.
So the gate starts conduction, but it does not normally stop it?
Correct. That is the key distinction. In a DC circuit, the anode current must be forced below the holding current, commonly by interrupting or commutating the current. In AC circuits, current naturally reaches zero each cycle, which can turn it off.
Okay, not the option I chose. It should be reducing its anode current below the holding current.
Yes, exactly. Once latched, an SCR remains on until its anode current falls below the holding current or it becomes reverse biased.
Okay, the operating condition is the part I need to hold on to.
Question 46. How does a VDR respond when the voltage across it rises above its normal level?
I said its resistance rises and opens the circuit. I mixed up a VDR's response with the behavior of a protective device that disconnects the supply.
Close in wording, but not in operation. Okay, let's slow the idea down. A VDR behaves the other way around.
High resistance during normal operation?
Yes, high resistance at normal voltage. When voltage rises beyond its characteristic level, resistance falls sharply, it conducts surge current, and the voltage is clamped. After the surge, it returns towards high resistance.
That means the correct answer is its resistance decreases sharply and it conducts surge current.
That's the one. A VDR has high resistance at normal voltage. During an overvoltage, its resistance falls and it diverts or absorbs surge current.
So when the voltage rises, the VDR's resistance falls and it conducts more surge current.
Question 47. In a single diode half-wave rectifier, what happens during the supply half cycle that forward biases the diode?
I selected current flows through the diode and load.
That answer is right. During the forward biased half cycle, the diode conducts and produces a load voltage pulse.
Yes, I'm happy with that point.
Question 48. Which statement best describes the operation of a single-phase half-wave rectifier?
It passes one half cycle of the AC input to the load.
Good, no problem with that one. A half-wave rectifier conducts during only one half cycle of each AC cycle, producing pulsating DC.
Yes, the circuit operation and the answer line up there.
Question 49. In a single-phase bridge rectifier, how many diodes conduct load current during each half cycle?
I counted 2 conducting devices.
Yes, your choice is correct. One diagonal pair of bridge diodes conducts during each half cycle, so 2 diodes carry the load current.
Right, 2 diodes conduct during each half cycle, one on each side of the load.
Question 50. Which components form the power circuit of a half-controlled single-phase full-wave bridge rectifier?
I chose a single transistor replacing the bridge. I knew control needed a semiconductor device, but I wasn't sure how a controlled rectifier is actually arranged.
I can see why you picked that, but it is not the right one. Let's work through it. A half-controlled single-phase full-wave bridge uses 2 SCRs and 2 ordinary diodes with the load completing the power circuit. Half-controlled means only half of the 4 bridge arms contain controllable devices. The firing angle of the 2 SCRs controls the average output.
So I should choose 2 SCRs, 2 diodes, and a load.
Yes, that's it. A half-controlled bridge normally contains 2 controlled devices, SCRs, 2 diodes, and the load.
I see, a half-controlled bridge uses 2 SCRs and 2 ordinary diodes.
Question 51. In a 3-phase full-wave bridge rectifier, how many diodes normally conduct at any instant?
My answer was 2, 1 device from the upper group and 1 from the lower group.
That one is correct. 1 diode connects the most positive phase to the load and another returns current to the most negative phase, so 2 diodes conduct at a time.
Yes, and I think I could draw a simple diagram to show it.
That's all 51 questions. Let's look at the pattern rather than only the score.
I was better with the basic definitions, but weaker when I had to picture current paths or remember what happens in reverse bias.
Good, you've got the important point now. Your main weak areas were surge suppression, safe insulation testing around electronics, rectifier pulse patterns, diode PIV selection, filter action, and SCR turnoff.
The 3-phase rectifier questions caught me too.
Yes, keep 3 facts together. 3-phase half-wave normally uses 3 diodes and needs a neutral return. 3-phase full-wave uses 6 diodes. In the full-wave bridge, 2 diodes conduct at one time and the output has 6 pulses per cycle.
So at 50 Hz, 6 times 50 gives 300 Hz ripple.
You read that question properly. Now give me the single-phase ripple figures.
Half wave is the same as supply frequency, so 50 Hz. Full wave is twice supply frequency, so 100 Hz.
Good. What about PIV?
It is the maximum reverse voltage the diode must withstand while it is blocking. The diode rating must be above the circuit PIV, with a margin.
Well done. And how do we turn off a conventional SCR?
Reduce its anode current below holding current or reverse bias it. Another positive gate pulse won't turn it off.
That's right. For your next attempt, first draw simple current paths for half-wave, bridge, and 3-phase bridge circuits. Then make a small comparison sheet for VDR, Zener diode, suppression diode, capacitor choke, and SCR.
And I should practice the ripple calculations without looking at the answers.
Yes, also explain each answer aloud. If you can explain why a distractor is wrong, you understand the topic more securely.
I still have work to do, but it feels less mixed up now.
That's the purpose of the review. Don't repeat the quiz immediately tonight. Take a break, then revisit the weak groups tomorrow and attempt it again after you can explain the diagrams.
Sounds good. Maybe a walk first if the rain stays away.
Good plan. A bit of balance helps. We'll check your next result and see whether those 25 errors have reduced.
Thanks, Roy.
No worries, Mira. Steady practice. You'll get there.